Hello all, let's start section 1.6. In 1.6, I will cover for you the laws of the limits. Um, if you remember the previous lecture, you calculated or estimated the limits of a function based on a table, approaching from right side, approaching from left side, choosing numbers, going close to the given limit, and you can estimate how much is the limit of a function, given function. In this section, we learn the laws of the limits, which makes our life much easier. Instead of using a table, directly calculate the limit of uh, a function that's given to us, any function, any type of function, trigonometric functions, algebraic functions, whatever function is, you will learn how to calculate those limits. Let me start with the basic laws. If I write it as a number one, your number one basic law, and I'll try to explain it also on a graph, which is not in your book. They didn't explain it in that way. They just put as a table for you. The first law of the limit says that the limit of a constant number, which C is a constant, always represents a constant, as x approaching to A always gives you a constant C. Why? What does it mean? Let's see a graph. Remember when you have the graph of x equals C from algebra, if you graph x equals C, it gives you always a horizontal line, correct? X equals C is a horizontal line. Now I have a point A. When I am writing limit of C equals C, that means as I'm approaching to A, as A is approaching to C, if I go this way, any point, you see on the Y, I have just this point. That's why the limit of a constant as X approaching to A is constant or C. Numeric example, the limit of 4 as X approaching to 3. Based on the definition, the limit of 4 as X approaching to 3 should be 4. Or another way of explanation, there is no variable there that you should plug 3 there. You see, there is no variable. You cannot plug 3 there. That's why it gives you back 4. The limit of, for example, negative 25 as X approaching to 2 will gives you back negative 25, whatever that number is. Correct? Now, rule number 2. The limit of X as X approaching to A. A is a number, right? What is the answer? If you remember the graph of X equal Y, the graph of X equal Y, it's a diagonal line like this. When X is 1, Y is 1. When X is 2, Y is 2. When X is 3, Y is 3, right? This line. Now, if I have this point as a, let's say A, or this point A, as I'm approaching to A, you see if I'm moving this way, approaching from the left or from the right, doesn't matter. If you're approaching from the right to A, how much is the value of A here? It gives you back A. If you approach from this side to A, it gives you back A. Then I can say the limit of X as X approaching to A always gives you what? A. For example, limit of X as X approaching to 5. My answer immediately 5. We use actually this rule a lot when we simplify big functions, correct? Soon you will see an example that I will use this rule. I'll plug in just my limit and I'll get my answer. These are the basic rules of limits. Now, based on this, I'll give you rule number 3, which your rule number 3 is the limit of addition. For example, if you have a function, a limit of a function of f of x as x approaching to a, the other day you saw the definition, it gives you L. And at the same time, you have another function, g of x, the limit of g of x. Let's say the limit of g of x as x approaching to a, but this a is the same number. Both of them, both these functions should approach to the same number. It gives you another number, for example, L1, L2, right? Then I can say, and their limits are exist. Now you know the meaning of when a limit can exist, when the limit of the right side and the left side, they are equal. On that time, you can say the limit exists. If their limit exists, then I can write my rule number 3, that the limit of f of x plus g of x as x approaching, for example, to a, I can separate these limits. I can write the limit of f of x as x approaching to a plus limit as x approaching to a of g of x. We call this rule the addition rule. Definitely, you can apply the same rule for subtraction. If you have the limit of f of x minus g of x, then it equals to the limit of f of x as x approaching to a minus limit of g of x as x approaching to a. This is rule number 3 and 4, basically. I put 2 of them together like this way, addition and subtraction. Number 4, limit as x approaching to a of f of x times g of x. Same as addition, you can write the limit as x approaching to a of f of x times the limit as x approaching to a of g of x. I will not do small examples here for you. When we start with big examples, I'll show you all these rules. Number 5. If I have the limit of f of x over g of x as x approaching to a, then I can write this one as a limit of numerator, which is f of x, as x approaching to a, over the limit of denominator as x approaching to a, which is g of x. But in this case, I have to say my denominator cannot be 0. That means I have to write the limit of g of x as x approaching to a cannot be 0. Correct? This one is also interesting. Number 6. If you have the limit of, for example, f of x to the power of n, a function to a power, as x approaching to a. The easy way is to put the limit inside. First take the limit of f of x as x approaching to a, then raise it to the power of n. Correct? Based on this exponent rule, then I can create another rule for another limit if radical gets involved, because we know radicals, they are actually exponents, rational exponents, right? If I have limit of n root of f of x as x approaching to a, then I can rewrite this as the n root of limit of f of x as x approaching to a. First take the limit, then raise the n root. Let me show you why. You see, if you have n root of x, for example, right? In exponent form, you can write this one as x to the power of 1 over n. That's this rule. It means I can apply this rule also for radicals. One more, property number 8. If you have limit of cf of x, right? cf of x, c is a constant as x approaching to a. What you do in this rule, it makes it easy, take the constant and bring it in front of the limit. Put c, then take the limit of the function. C limit of f of x as x approaching to a. My recommendation for you, of course, this semester is an online class. You may have a kind of cheat sheet with you to put these rules, but limit goes with you all the way, even if you go to next semester calculus 2, next semester calculus 3, if you go to differential equation class, you always need limits. It's with you, it's staying with you. And the laws are not so difficult. Try to memorize them, try to understand them. The limit of addition, I can write as a 2 separate limits, right? Subtraction or division or multiplication or power or radical. There are 8 easy rules that you have to memorize. This table is on page number 62 of your book. Not all of them, some of them, because some of them is on other pages. You can find this laws on your page 62 of your book. Now, I'll start with easy examples. Then I do tonight in this lecture a lot of examples for you. I'll show you other rules also. Then we go slowly talk about other ways of finding limits, right? Let's start with a simple example. Example number 1. For example, I have a function limit as x approaching to 2 of x cubed minus 2x plus 7. At the beginning, try to apply the rules, please. I know in future you will learn other techniques that you don't need to go like too many steps. Even in one step, you can find the answer for your problem. But at this time that you are learning the rules, please apply all rules. First, you see, you have here x cubed minus 2x plus 7. You can apply the addition and subtraction rule. It means you can write this as a limit of x cubed as x approaching to 2 minus limit of 2x as x approaching to 2 plus limit of 7 as x approaching to 2. Now, in the first part, you see, you can apply your power rule here, f of x to the power of n. Then you can write this one as a limit of x as x approaching to 2 all to the power of what? 3. Minus, in the second part of the problem, you have a constant of 2. Which rule was that? Number 7 or number 8 that I talk about constant, right? Or maybe number 5. Let's see which one. Number 8. You have CF of x. You see here, CF of x. Then you can write this one as a 2 limit of x as x approaching to 2. Plus limit of 7 as x approaching to 2. One more thing, because it's the beginning of the limits, please write the sign of the limit, the symbol of the limit, up to the last step. When you plug in your number to the variable, that's the time that you are not writing the limit symbol. If you don't put the limit symbol here, in this step, your problem is totally wrong. You have to show, you have to keep the symbol, right? Now let's simplify. Limit of x as x approaching to 2. We had a rule for it. Limit of x as x approaching to a gives me always a. It means limit of x as x approaching to 2 gives you 2. And you don't need to write the limit symbol anymore because you plugged in your number. And you have power of 3, it means 2 cubed. Minus 2 times limit of x as x approaching to 2. Again, same rule. I'll plug in 2, it means 2 times 2. Plus limit of 7 as x approaching to 2. We had a law for that. Limit of constant. If I have limit of c, x approaching to a, it gives me back c. It means here limit of 7, x approaching to 2 gives you back 7. Now, easy, calculate. I'm sure everyone can calculate. It gives you 8 minus 4 plus 7, which gives you what? I think 11. Correct? Laws of limits makes the problem easy for you when you apply. Later, I'll give you another rule of the limits that's much, much easier. You can avoid all these steps and directly you can find the answer, but it has a kind of understanding of that because students are using that law for all limits and their answer goes wrong sometimes because they don't focus. Later, I'll explain it to you and I'll show you that method also. Let's do another example. For example, let's say this one is good from your book. Example, limit of 2x squared minus 3x plus 4 as x approaching to what? As x approaching to 5. Again, applying the rules of the limits, correct? Limit of subtraction and addition, separate all of them. You can write limit as x approaching to 5 of 2x squared minus limit of 3x as x approaching to 5 plus limit of 4 as x approaching to 5. Now, here you see two rules comes together, a constant and also the exponent rule. Then I will apply both rules, make it easy for me. 2, right? Parentheses or bracket, limit of x as x approaching to 5 to the power of what? 2. Minus, again, constant, 3 limit of x as x approaching to 5. Plus limit of 4 as x approaching to 5. Now simplify. Keep the 2, which is outside. times limit of x as x approaching to 5 gives you 5 because you have a square, but the square here. Minus 3 times limit of x, x approaching to 5 gives you 5. Plus limit of a constant is constant. Limit of 4 as x approaching to 5 is 4. Now simplify. Hopefully, you will not do this mistake to first multiply, then raise to the power. First raise to the power, then multiply. 5 squared 25 times 250 minus 15 plus 4, which gives you 54 minus 15, which is negative 30 or positive 39. Easy? Let me show you another example also. Example, let's say limit of square root of 2x plus 5 as x approaching to 2. I gave you a rule for the radicals, right? If you have the limit of n root of f of x, what you do as x approaching to a, you put the limit under the radical. That means n root of limit of f of x as x approaching to a, then take the radical, right? Let's apply the rule here. Then this one equals square root limit of 2x plus 5 as x approaching to 2. And now under the radical, you see you have the addition rule. You can separate them, right? Because you want to practice with limit rules. Then you can write this one as a square root limit of 2x as x approaching to 2 plus limit of 5 as x approaching to 2. Again, here constant rule. You can write square root 2 limit of x as x approaching to 2 plus limit of 5 as x approaching to 2. Now simplify. It's equal square root 2 times limit of x as x approaching to 2 gives you 2 plus limit of 5x approaching to 2, limit of constant is constant, it means plus 5, which gives you square root of 9, which gives you what? 3. This is how you apply the limit rules, correct? There is another method that you can use for your limits, and you can find easily limits of some functions, not all of them, correct? I gave you that rule right now, but try to practice with these rules also, correct? We have a rule by name direct substitution. What is the rule of direct substitution? Let me see which page in your book is that one. If they have it, because sometimes they use it, but they don't show as a rule in your book. Hopefully, if we have in your book. In which page? Because most of my lectures, I just lecture for you, even I am not looking to your book, which page you have it. Here, on page number 65, they explain another rule of the limits, which we call it direct substitution. What is direct substitution? Substitution or property or law or method, correct? If f of x or f, a function f, is a polynomial or rational function, and A is in the domain of f, then you can write the limit of f of x as x approaching to A is actually finding f of A. What does it mean? I want to translate it a little bit for you. Maybe you already got it. The limit of f of x as x approaching to A equals to f of A. It's the same thing that you find the f of A. But what does it mean? The last part of this definition is important. When you are dealing with a polynomial or a rational function or any other function, when this number A is in the domain of your function, which is f, for example, if I have limit of 2x minus 5 as x approaching to 2. If you see your function here, it's a polynomial function. Is 2s in the domain of 2x minus 5? Remember the days that I covered the review for you, I had a lecture on the domain of the functions also. The domain of polynomial functions starts from negative infinity to positive infinity, right? And definitely 2 is between here in this set, correct? And this domain. Okay, if 2 is in the domain, now instead of applying all rules of the limits, right? To first write as a subtraction, then take the constant to the front, going 3-4 step. Instead of doing that, what I do, immediately I look for the f of 2. Immediately look for the f of 2. If this is a function, what is f of 2? F of 2 means 2 times 2 minus 5, which gives me 4 minus 5, which gives me negative 1. You see, this is easy. And if you don't believe, let's apply the rules. You will see we will end up with negative 1. Limit of 2x minus 5 as x approaching to 2. If I go applying all rules, I will write 2 limit of x as x approaching to 2 minus limit of 5 as x approaching to 2. Here, if I plug in 2 times limit of x approaching to 2 is 2, minus limit of 5 as x approaching to 2 is 5, which gives you negative 1. See? Instead of doing all these steps, immediately look for the f of 2, because 2 is in the domain of the given function. Another example. Limit of x squared minus 9 over x minus 1 as x approaching to 3. Based on the laws, you have to take the limit of numerator, then apply the subtraction rule, then limit of denominator, then apply the rules of the limit, then at the end you can find the answer. But here, can I use direct substitution? Or because you saw there in the definition, if it's a polynomial and rational function, yes, I can use direct substitution. You may, but you have to check, make sure that this given number as x approaching to 3 is in the domain of this function. Remember the day that I explained rational functions for you, I told you that rational functions, they have a restriction. There is a number that if you put in the denominator becomes undefined or zero. That's your restriction. First, find your restriction. What is your restriction here? X minus 1 equals 0. It means x equal 1. Okay, x cannot take 1 because 1 is your vertical asymptote, right? Then 3 is in the domain, because if you write here the domain for this function, here is 1. You circle 1. You cannot take 1, but you can take all these values and all these values. It means your domain is from negative infinity to 1, union from 1 to infinity. That means 3 is in the domain, right? Then use direct substitution. Look for the f of 3. F of 3 means 3 squared minus 9 over 3 minus 1, which gives you 9 minus 9, 0 over 1 over 2, which your answer is 1, 0. Now look how direct substitution makes your life easy, because if I solve this problem based on the rules, I have limit of x squared minus 9 over x minus 1 as x approaching to 3. I will rewrite this one as a limit as x approaching to the 3, x squared minus 9 over limit of x minus 1 as x approaching to 3 based on the quotient rule. Now in the top, I have subtraction. I can separate those. I can write limit of x, even if I apply both rules because I have exponent also, as x approaching to 3, then to the power of 2 minus limit of x approaching to 3, 9. Denominator, same thing. Limit of x as x approaching to 3 minus limit of 1 as x approaching to 3. Now simplify. In the top, limit of x as x approaching to 3 gives you 3 square minus limit of constant over limit of x as x approaching to 3, 3 minus limit of 1, limit of constant, which gives you 0 over 2, which is what? 0. We use a lot direct substitution, but we have to be careful. Again, I'm repeating. If this limit, the number that you are approaching, if this number is in the domain of the given function, you can use direct substitution. If it is not in the domain, please do not use direct substitution because your answer will be wrong. For example, look at this example. Another example. Limit of x squared minus 1 over x minus 1 as x approaching to 1. Can I use here direct substitution? Oh, let's see first the domain. Let's see first the restriction. X minus 1 equals 0, x equal 1, it means x cannot take 1. You cannot use direct substitution because if you plug in 1 here immediately, denominator becomes 0. You cannot go to find f of 1. No way to use this method. There is another method that I will explain in the next example for you, right? But you have to be careful when you're using direct substitution, careful. Because this rule is easy, right? And right now everyone is saying, yeah, professor, you should give us this rule instead of 8 rules. But you cannot use it all the time, right? Only if your number is in the domain, you can use it. Now, to finish this example, let me explain something else to you. There are some limits that if you plug in your number immediately in the function or using direct substitution, you will see your denominator becomes 0. then how to deal with those problems. One method was table, right? Because it's not necessary to exactly plug one. You go really, really close to one, but not one, correct? That was the method. But how to deal with this problem? Use techniques of algebra to simplify. I will rewrite the problem and I'll explain it to you. Any techniques of algebra that it works. Limit of x squared minus 1 over x minus 1 as x approaching to 1. Look at this fraction. What you can do here? What you can do here? Can I factor the top? Yes. Then let's factor. Limit of x plus 1 times x minus 1 over x minus 1 as x approaching to 1. Here, x minus 1 cancels out with x minus 1. Now, limit of x plus 1 as x approaching to 1. Here, can I use direct substitution? Definitely yes, because it's a polynomial and the domain is from negative infinity to positive infinity. 1 is in that domain. Then I'll use direct substitution. It's equal 1 plus 1, which is what? 2. You saw this example before, the day that I started with limits using the table. Right? But this way is now much, much easier for you. Let's take another example. I'll do tonight in this lecture a lot of examples because I want to show you. I'm saying always tonight because I'm recording this lecture at night time. That's I say all the time tonight. But for you in this video, I'll do a lot of examples for you to show different types of them. For example, limit of 3 plus h all square minus 9 over h as h approaching to 0. You see, if you use direct substitution, check first. When you deal with limit, always check first. Plug it first, the number, and see what's happening. If it's undefined, then you're okay. If it becomes undefined, then you have to use the technique. First, always check when you are dealing with the problems. It means, check means plug in the number. It gives you 3 plus 0 all square minus 9 over 0. Wow, even I'm not simplifying the numerator. Here is the problem. I cannot use direct substitution. Then how to deal with this problem? Can I simplify the top a little bit? The only way, the only algebra that I can do here is to simplify the numerator, right? Then limit of, what is 3 plus h squared? Some of you, maybe your professor in algebra class told you to do this. It's okay to do this. I'm also telling you it's okay to do this. 3 plus h squared means 3 plus h times 3 plus h, and you can simplify. It takes another half page or a lot of time to simplify. But if you remember, you have the formula a plus b squared means a squared plus 2ab plus b squared, right? Use this technique easily because now you are in calculus class. It means 9 plus 6h plus h squared minus 9 over h as h approaching to 0. Positive 9, negative 9 cancels out. Then you can write limit as h approaching to 0 of 6h plus h squared over h. Now, what's next step? Still, if you plug in, you see you become denominator becomes 0. The whole goal or idea is that the denominator should not become 0. It means you have to remove that h from the denominator somehow. But how? You see, can you factor the h at the top? H is common between these two terms. Then you can write limit as h approaching to 0. factor out h. Inside it will be 6 plus h over h. Now this h cancels out with this h. I'll show you something. Please, please, you are a calculus students. Don't do this here, right? You have to be in factor form that to could reduce. You cannot reduce here. Please do not do this. When I'm saying these words to you, it means my experience talks with you from different classes. You do this mistake a lot. It's not the time to do these algebraic mistakes here. It's a calculus class. Now you can simplify. You end up with limit of 6 plus h as h approaching to 0. Now you can use direct substitution. It means 6 plus 0. Your answer is what? 6. One more example. Limit of square root of t squared, why t, let's say it x squared plus 9 minus 3 over x squared as x approaching to 0. In your book, instead of x, they use t. Writing t is kind of, for me, why not x? It can be any variable, right? I just change it to x because I'm faster with x. Now, if you use direct substitution here, if you plug in 0, you see denominator becomes 0 and at any case, right? Here, denominator becomes 0. 0 square 0, then you cannot use direct substitution. Which method of algebra you should use here to rewrite this? You have limit square root of x squared plus 9 minus 3 over x squared. What should I do? What can I do? Which method of algebra? I told you, those of you that you have good grades in algebra, this class is easy. Do you remember we had a topic in algebra, rationalizing the numerator or rationalizing the denominator? To rationalize a numerator or denominator, if you have a binomial, which your numerator here is binomial, right? You have two terms. It's a binomial. You have to multiply the numerator and denominator by the conjugate of your numerator. What is conjugate? I'll give you a little bit of algebra. Remember the day that you had, if you multiply these two parentheses, x plus a times x minus a, remember this product? It gives you x squared minus a squared. The right side, your professor explained it to you as a difference of squares. The left side, we call these two conjugates. Correct? X plus a is the conjugate of x minus a. X minus a is the conjugate of x plus a. Now, what is the conjugate of numerator? The conjugate of numerator is x squared plus 9 plus 3 over same thing, x squared plus 9 plus 3. Multiply the top and bottom of this fraction with the conjugate of numerator and try to simplify. Back to black color. Keep the limit symbol, limit as x approaching to 0. What is the square root of x squared plus 9 times the square root of x squared plus 9? The square root cancels out. It means you end up with x squared plus 9. Negative times positive gives you negative because you are again applying this rule, right? You see, x plus x minus a times x plus a. It gives you x squared minus a squared, right? It means minus 9 over
keep the denominator the way it is. X squared, square root of x squared plus 9 plus 3. Negative 9, positive 9 cancels out. Then you end up with limit of x squared over x squared times square root of x squared plus 9 plus 3 as x approaching to 0. You see here, you can cancel out x squared with x squared. The problem was that x squared in the denominator. That was the problem. You removed it. Correct? Now I'll end up with limit as x approaching to 0, 1 over what left in the denominator, square root of x squared plus 9 plus 3. This x squared under the radical is not anymore a problem for me, because here I have plus 9. If it was times 9, again, and here times 3, again, it was a problem for me. But no, now you're adding, right? Plug in the number, it gives you 1 over, you are not writing any more limit, square root of 0 squared plus 9 plus 3, which gives you 1 over. Square root of 9 gives you 3 plus 3, which gives you 1 over what? 6. Final answer. If you have radical in the denominator, multiply the numerator and denominator by the conjugate of denominator, correct? These are few methods that I show it to you, a few examples that works very well. And we are done with the laws of the limits here. Now, I'll explain 2 more theorem for you. One of them, we call it a squeeze theorem. What does it mean? And the other one, if you have 2 functions and you compare these 2 functions, what does it mean, right? Theorem number 1, or here in your book, they put it as a number 2, number 3, because they have another one also. Anyway, who cares about numbers? If you have a function f of x less than or equal to another function g of x. One function smaller or equal to the second function. In this case, this theorem says that the limit of f of x as x approaching to a definitely will be less than the limit of g of x as x approaching to a. If you want to see it in a graph, I can show it in a graph for you. What does it mean, this theory, right? This is x, this is y. Let me draw a function, for example, this function, let's name it g of x. And I'll draw another function. Let me change the color. Color hasn't changed. I wish we were in a face-to-face class. For example, let's say something like this. Let's name this red function f of x. And a point here, A. You see, your g of x is greater than f of x because the graph of g is above the graph of A. It means the function g of x is greater than the function f of x. Now, is the limit of f of x as x approaching to a should be less than the g of x? You see, when you are approaching to a, this is the limit of f of x as x approaching to a. For the g, same way, if you approach to a, this is the limit of g of x as x approaching to a, Which number is greater, this one or this one? Definitely the one above, right? Then this theorem exactly is a correct theorem. When you compare two functions, and one of them is less than the other or equal to, then this theorem or this law or this property works very well, correct? Their limits has the same relation. Next theory is the squeeze theorem. What is the squeeze theorem? Consider three functions now. Let me graph it for you. For example, you have three functions. X, Y. For example, you have this relation. F of X is less than equal G of X and less than equal, let's say, H of X. Three functions. I'll draw it now. Let's say something like this. This is F of X. Let's draw a red function. I'll name this red line or red graph H of X. And let me use another color, for example, maybe green. Let's draw the G of X. This is your G of X. You see now the relation F of X less than equal G of X, F of X is less than G of X, and G of X is less than the H of X. What the squeeze theorem says, if you have a function in this relation that G of X is between F of X and H of X, you see this point? You can write from here, and you have another relation that the limit of F of X as X approaching to A equals to the limit of H of X as X approaching to A. You see, I brought both of them in one point. It means the limit of F of X and the limit of G of X, they are equal. It means they meet at one point, correct? If you have this relation, immediately you can write from here, and this one is, for example, L, a number, here L. Immediately you can write from here that the limit of G of X as X approaching to A is L. Whatever this number is, G is forced to have the same limit because it's in between, it's squeezed, right? It's squeezed. That's why it's forced to, it has the same limit. That's what we call the squeeze theorem. Which kind of problems you are dealing in this theorem with, correct? Let me show you an example using the squeeze theorem to find limits. For example, which example is a good example? Limit of x squared sine of 1 over x. This is my sine. Again, my bad habit. Sine should be right like this, but I'm doing like this. This is my sine. This is my limit. Maybe you laugh or you ask me which one is sine, which one is limit. There is a slight difference between my writing, because limit I should write this way, but I can't somehow. Sine I should write this way, but I always do this. This is sine, this is limit, okay? Limit of x squared sine of 1 over x as x approaching to 0. They're asking you to show if the limit of x squared sine of 1 over x as x approaching to 0 is 0. Show, it means proof that this limit becomes 0. This limit becomes 0. What you do, we know the graph of the sine, right? The graph of the sine, the highest point is 1, the lowest point is negative 1. That means the sign of the numbers, I'm hoping that your trigonometry professor explained it well to you, that all the values of the signs of the numbers or the angles, it's starting from negative 1 to 1. You don't have the sign of an angle 2 point something. It's always between negative 1 and 1, right? Because of the graph. We know that the sine of 1 over x has values less than equal 1 and can take values greater or equal negative 1. Correct? Agree? Because of this graph? Because the graph starts like this. It goes down like up between negative 1 and 1. Now, let's solve this inequality. Let's solve it. To solve this, can I multiply both sides of this inequality by x? Then I will end up with negative 1 times x less than equal sine of 1 less than equal 1 times x. Negative 1 times x gives you negative x, correct? Less than equal sine of 1 less than equal x. Now, if I apply here the limit rules, correct? If I apply the limit rules, can I write the limit of x squared, which is the first part of your function here? The limit of x squared, but based on the product rule, right? As x approaching to 0 gives me 0, agree? Also, the limit of negative x squared as x approaching to 0 gives you 0. You see, that is 0, then can I write the limit of x squared sine of 1 over x as x approaching to 0 is 0? Because 0 times this gives you 0, right? And actually you prove that this limit is 0. This is the only example in your book about the squeeze theorem, and my lecture was actually tonight too long. I'll stop the lecture here, but in my next lecture, before I should talk about continuity, I will do a few more examples for you to show how you are using the squeeze theorem to find the limit of the third function. I'll bring more examples for you. Unfortunately, this is the only example in your book. Excuse me. But in my next lecture, definitely, I will cover a few more examples for you. This was all about section 1.6. I'll stop the lecture here. You don't have 6.7. I will jump, not 6.7, 1.7. Your next lecture will be 1.8. Then see you in your next lecture.